Thanks for allowing me to talk here at the CHEMTalks. That's a nice tradition that I hope to well, fill in as good as the previous speakers here. That's right. My name is Jack Pedersen. I'm a postdoc here at the Department of Chemistry at the University of Copenhagen. I'm part of the Center for High-Entropy Alloy Catalysis, which is funded by the Danish National Research Foundation. My contacts are here, and my talk will be about this energy transition that we are ahead of in society, and how these high-entropy alloy catalysts may help with that. So let's get to it. This is the agenda for today. First, encouraged by Christian, I'll tell you about my journey to where I am now. Then I'll just motivate what we're doing, and then I'll tell how electrocatalysis and high-entropy alloys may be the solution for the climate issues we're facing. And then I'll give you two highlights of our research into these composition spaces that these high-entropy alloys give. And finally, an outlook. So I'm a postdoc here at the department. I've actually done my bachelor's. Well, let me start in the beginning. I started here at the department in 2013. I did my bachelor's in chemistry. I did my bachelor's project with Stefan Sauer, a professor at the department. And then in 2016, I started my master's in physical chemistry, also here. And I went on a short exchange semester during that. And that's where I started my collaboration with my supervisor, Jan Rosmeisel. I did my master's project. That was actually where the journey of high-entropy alloy catalysis began. That was back in 2017. And then following my master's, I continued in a PhD project in the same research area. During that, I went for a research stay at the Hong Kong University of Science and Technology. I defended my PhD in 2021. And after that, I continued as a postdoc, and that I've been for 2 years now. And yeah, that's my journey in academia. What's ahead? Well, that's a mystery. Let's get to the science. This number, 0.95, is the temperature change since the 20th century average that I calculate when I look at the data. And so this is a monumental increase in global temperature, and that gives rise to all these extreme weather events that cause an existential threat, essentially, to humanity. So this is what we're fighting against. Getting this number down, essentially, is what we're trying. Why is that number increasing? Well, at the same time as temperature has been going up, greenhouse gas concentrations have also increased. So carbon dioxide shown here in between 1959, where we started to measure those, and 2022 has increased on average by 0.25% per year. And the ratios are more or less the same for other active greenhouse gases. Methane has also increased, and nitrous oxide has also increased since we started measuring those at about the same rates, a little less than 1% per year. Why have these greenhouse gases increased in the atmosphere? Well, the explanation lies in how our energy landscape looks. This was the primary energy consumption of the globe in 2022. We consumed 604 exajoules. And of those, 82% were fossil-based, oil, natural gas, or coal, while only a fraction of that was you can say, non-emitting energy sources. Here, renewables, hydroelectricity and nuclear energy. So that's the explanation. If you look at where the emissions come from more specifically, you can divide it into these fractions. The energy sector is responsible for about 75% of the emissions, so of combined greenhouse gas emissions. And if you look a little close at what the energy sector is, it's the energy used in industry for manufacturing all the products that we enjoy every day. It's for transportation. It's to warm our buildings and for electricity in buildings. And then a non-substantial part is also fugitive emissions, simply methane leaking from the grid. Other big parts of this emission diagram is agriculture, forestry. There's some waste combustion, and there is some industrial processes that inherently emit carbon dioxide. One example is cement production, and there are other chemical manufacturing methods there as well. So this is where the multifaceted challenge comes in. These are some of the emitters that I could think of from the division we saw before, and I'll try and propose some solutions for the future. Whenever possible, if we can electrify our energy consuming processes, that will be advantageous, because direct electrification skips the step of having to store energy. It reduces losses immensely. So if you can run your reactions electrochemically, for instance, with direct renewable electricity, that will be a huge advantage for emissions. And then some transportations might also be able to run directly on electricity. Trains, we know can do this. And domestic energy use for electricity and heating can also be based on direct renewable electricity. But directly renewable electricity has some disadvantages. The sun doesn't always shine, and the wind doesn't always blow. So sometimes that needs to be stored, that energy. That can be done in multiple ways. One way is in batteries. We could put batteries on cars and some trucks. We could also have domestic batteries to heat our houses when we don't get electricity directly from the grid. So that might be a solution in some cases. There are more solutions because batteries have an enormous disadvantage, and that is the energy density in them. It is very low, so you need very big batteries if you need a lot of energy. So in some cases, fuels in the form of chemicals could be necessary. They are very more energy dense. We have, we know of the hydrogen fuel cell. There you can operate or generate electricity from hydrogen and oxygen. You could put such a fuel cell in some uses. In other uses, you might want to use another fuel, something like ammonia, if it has to be non-carbon based. We have seen that, or that is being developed for ships. And when you need very energy intensive energy sources, because you need high temperatures, for instance, you might also need fuels instead of batteries, and maybe even instead of direct electricity. Then there are the carbon fuels, those that we're actually trying to avoid. But if we can make them from sustainable sources, that is non-fossil sources, then they could actually have a role to play in the future of the energy landscape. And they have the advantage that they fit right in the infrastructure we have already, and they are very energy dense. And there's a lot of variability in the fuels you can make here, because carbon has a very diverse chemistry. You can make diesel and gasoline. That variability is not available in nitrogen's and hydrogen's chemistry. So that provides a lot of advantages. That provides that you need to capture some CO2 and be able to react that selectively, and that's not so easy. And then another thing we can do in our energy landscape is when we have to reduce metals, which we use a lot of in construction, we could do that from hydrogen instead of carbon, which is done currently. We reduce a lot of iron and aluminum every year from oxides. That could be done with hydrogen. So these are some of the solutions. There are many ways, and the final energy landscape will probably be a combination of these, hence a multifaceted challenge. So here you see a plot of the energy produced in Denmark. The top plot is for last week's energy production. There was a lot of wind, so we had a lot of wind energy. That's the green area. There was not so much sun, and we had to import a lot of energy. That's the black areas under the consumption curve, which is the white curve at the top. We also burned a lot of fossil fuels. There was a constant supply, almost constant supply of fossil fuels. That's of course what we want to replace, and we want to build out more renewables so that we can fill out these gaps when consumption is higher than the production. I show for a comparison a day or a week in this summer. We use generally a little less power during the summer, and we have more sun. On the other hand, we don't have as much wind. But ever so often we have these peaks where we produce more power or more electricity than we consume. If we could use that to store it for later, that would be the way to replace the fossil fuels. So this is where chemistry comes in. Power to X is a broad term. It means to transform power into something else, and this something else is something energy rich. So in the future of the energy economy, we need to, instead of fossil fuels, get our fuels from other chemicals. We also need a chemical reactants for the chemical industry to make plastics and so on. Carbon, the most abundant, or the most renewable source of carbon is in carbon dioxide. So we'll have to capture those from the air, reduce them with electricity and water, or the hydrogen from water, to get these reduced compounds, ammonia, for instance. This power-to-X process could also be simply charging a lithium-ion battery, where lithium goes from cobalt oxide into graphite. Now, when the sun does not shine or the wind does not blow, we can actually just mirror this whole process. And instead of producing these chemicals, we can consume them. That could be in a fuel cell that generates electricity, or it could be in a combustion engine in a ship or in an airplane. And essentially, you can reverse all the processes. You can make a rotor spin. That would be the case on a ship, or you can make photons that you captured from the sun now as a light bulb in your house, for instance. Then you emit all these renewable but now oxidized chemicals, and then those you'll have to recycle again. So if we zoom in a little on the chemistry that goes on in these devices that we need, we can look at the electrolyzer we saw before. We now get electricity from a windmill or a solar panel. And this is also where the catalysis becomes important. So we need to oxidize water to oxygen. In the best catalytic theories we have, we assume that the water adsorbs on the electrode surface with the help of a catalyst. Proton gets transferred through a proton exchange membrane, and the electron is, you can say, pumped with the potential provided by the renewable energy into the to the cathode, where it can later recombine with the hydrogen atom to form hydrogen in molecular form. The OH molecule from water here is then further oxidized now to an oxygen atom on a surface. The proton and electron gets transferred to the other electrode. And to make oxygen, we need another water molecule that needs to bind to this oxygen atom. It does that under the release of a hydrogen ion, so a proton, and the release of an electron. That gets transferred to the other cathode, and we continue this oxidation until we have a molecular oxygen. Now the hydrogen can combine on the cathode to molecular hydrogen, and this is essentially how the electrolyzer device works. Water here could be replaced by other chemicals. It could be nitrogen, or it could be CO2, for instance. The process is very similar. So what is the role of the catalyst in this, and how do we go about making them better? So a catalyst can very roughly be, but very conveniently, be described by this model, this Sebastian model. And it's very easy to understand, because to make a catalyst work, you must not bind your intermediates too strongly nor too weakly. If you bind too strongly, you'll never be able to release them from the catalyst surface. That's simply too stable. And if you will not even be able to absorb them in the first place, as with the water we saw in the previous example. So every traditional catalyst has a single value on this curve. A pure metal like this one has a given absorption strength that can describe its catalytic activity. Now, when you start alloying, you provide more possible sites for these reaction intermediates, and you now get multiple points on this activity curve. What also happens when you start alloying is you broaden these distributions of these properties. Before they were discrete values, now they're perturbed by the environment around the atoms. It's a ligand effect, you can say. The new thing about high-entropy alloys is you can continue doing this, and you get more and more absorption sites, and you broaden your distributions more and more as well. So while you do that, you increase the likelihood of finding something at the peak of this curve, where the activity is highest, where the absorption energy is best, and the activation barriers are lowest. You do that at the cost of other sites that are inactive, but the other sites help perturb this absorption strength to something that is near optimal, and you get this near continuum. That's the unique thing about these high-entropy alloys. So high entropy is what I keep saying. A high-entropy alloy is essentially a high-entropy state of a many metal alloy. So here I've shown what could happen if you mixed some pure metals. They have a very low entropy state. You could make what we want to get this broadening of these absorption energy distributions is a high-entropy solid solution, where they're randomly mixed together. This depends a lot on the synthesis method, which of these scenarios you get. One thing you can get also is perhaps also more stable, where some metals want to form an intermetallic phase, something that is ordered and therefore does not have this broadening of these distributions. So we cannot tune the properties so well, because they're very discrete even in these systems. And then you can have that mixed with a solid solution of some other metals that like to mix more. And then another case is you simply have your original metals with the other metals mixed in smaller fractions. That's the common case actually in the catalytic field. So it depends a lot on synthesis, what case you end up in here. And hydrobalance will likely only be metastable, but if they are so on a time scale that's long enough for it to be feasible economically, then we're happy with that. So hydrobalance, you can sort of imagine it as a composition space. At the vertices of such a tetrahedron here, you have the pure elements. On the edges, you have the binary alloys. And that's where most research efforts have been focused, because they're more likely to be synthesized and more likely to be stable. In the middle of this composition space, we don't know very much. And that's the space, that's the part of the space with the random and very diverse mixing of elements. And this space, it grows in dimensionality with the number of metals, hence the multidimensionality. I'll go through 2 studies where we looked at these very high-dimensional composition spaces. The first is where we looked at a 5-element composition space for the oxygen reduction reaction. So this half-cell reaction where you reduce oxygen gas to water, that's relevant in the hydrogen fuel cell. But it's also a very well-studied reaction, and that's why we're taking that as our initial steps. And we included 5 metals, silver, gold, copper, palladium, platinum, mixed them together randomly in simulations. The next example I'll show you is for an experimental study. But here first for simulations. So you can, with our simulations, we can, and the theory I described before, we can map out the activity function of this composition in its composition space. And you can imagine the red points being active, the blue ones being inactive. But describing this function inside this composition space is a very new thing. We can look at where there are optima on this function in 4-dimensional space where this exists, and we can then later suggest that for experimentalists. The thing about this high dimension is that it's very difficult for an experimentalist to try and search through the space. The reason is that there are so many possibilities. I think in this plot there are some 10,000 samples that we have simulated. Doing 10,000 experiments is not very feasible. So in this study, we try to investigate how many experiments are reasonable to before you have enough knowledge of your space. So here's a toy example. This shows the process of Bayesian optimization. We have a target function on the left. It's a composition space composed of 3 arbitrary metals. And on the right, we have an iteratively updated surrogate function of this space that is updated every time we sample a new point. What we're interested in knowing is how many samples do we need to know all the important points? And that would be the optima in this space. And in this little toy example, we have a decent description of the whole space after 17 samples. Then we know all the optima, and we're happy about our knowledge of the activity function. So this we did with we developed a model for describing the catalytic activity of the oxygen reduction reaction on these 5 metals. We did what an experimentalist would do and take 1 sample at a time, picking the next one intelligently. That is with a trade-off between the exploration and the exploitation of the activity function. We find we know the ground truth here because it's simulation, so we know that the optimization found 1 local optimum after 15 samples with these 5 metals. It found one of the other local optima, an iridium platinum binary alloy, after 28 samples. And the global optimum in this study was a silver palladium catalyst. We found that on average around 50 samples. There's an error bar there of plus minus 20 samples. But that and then after those 50 samples, not much happened to the composition space. The morphology of it remains rather the same. The important point in the study was that 50 samples is indeed way more feasible to sample than the 10,000 that I showed in the plot before. You can plot the evolution of this sampling as the white curve here, the number of samples on the x-axis, and then the catalytic activity on the y-axis, where more negative is good, it means more current. And you can see how it identifies these three local optima that were present in this composition space. Another thing we get out of this analysis is the length scale, the correlation length of this activity function. We can determine that to be around 0.3. And this is a space that goes between 0 and 1. Those are the atomic molar fractions. And that directly correlates with the number of experiments that are necessary to find the knowledge about the composition space. The longer this length scale, the less experiments are needed. And that might vary with reactions. The second study I want to highlight is one primarily conducted by Vladislav Mintz at the University of Bern. The same reaction, oxygen reduction reaction, now on 8 elements. What Vlad Mintz did was he sampled 350 different compositions within the space. Here are shown 200 of them. And then for each of those samples, he did a linear sweep voltammogram where he reduced the oxygen to water for different compositions that he also determined. This took a long time, but it provided us with a lot of knowledge. The knowledge we gained here was that you can actually sample from a very high dimensional composition space and get knowledge about the sub-dimensional composition spaces. So using all these 8-element catalysts that he produced, we could make predictions on the 5-element catalyst composition spaces with as much prediction power as we have in the 8-element composition space itself. And this is remarkable because the 8 elements were sampled inside a composition space. And in this composition space, the 5-element alloys are on the edges and vertices, like in that tetrahedron we saw previously. So this is nice. We determined also a global optimum in this composition space for the oxygen reduction reaction. That was a gold, osmium, palladium, platinum alloy. When we use the 5-element model, we get so a model conducted or devised from experiments of 5 elements instead of the 8. We found a very similar optimum to the one with the 8-element model. So I'll finish off the talk with a short summary and outlook, some takeaways for you. So the thing about hydrogen catalysis, that it is a new paradigm in our field, that we can start in the middle of a composition space instead of on the edges. That provides a whole new way of tuning catalytic properties. And that is exactly what the high-entropy alloys can do. And we can now navigate it also with intelligent methods and for more reactions also. And there are many more to be found, but that's good because the catalytic field is trying to include more reactions to model. And then to make this really powerful, there's ongoing work also in the group to try and include the catalyst metastability in these models, so that we can also start using more abundant metals than the very precious metals that I've shown you so far. And with that, I'll acknowledge the funders that is mainly the Center for High-Entropy Alloy Catalysis, but also the structure of materials in real time that sponsored me during my PhD. And for the research in this study, I'll thank these people, Christian and Jan, and Ladislav Mintz and Matthias at the University of Bern, and our collaborators from the Ruhr University Bochum, who are also helping out with experiments. And thanks to you for your attention.